Here we have another video about exponent rules, this time simplifying radicals with higher order roots. If you missed the other video about simplifying radicals with square roots, you'll probably want to go back and watch that video before this one. And if you remember from the square root video, there's an invisible 2 in the little hook, and when we're talking higher order roots, that just means we have a larger number than 2 in that hook of the radical. For instance, third root, fourth root, and so on. And notice we have 3 examples simplifying numbers and 3 examples simplifying variables. For the number examples, we're going to approach these the same way as we did in the square root video, where for this example, we're going to take that 81 and split it into the factors that multiply to make it. For instance, 9 times 9 is 81, and 9 can be broken down into 3 times 3. And so we can continue to split the other 9 in the same way. And when we're doing this, we want to continue to split each number until we break it all the way down until a number can't be split up anymore. For instance, there's nothing else that multiplies to make 3 besides 3 times 1, so 3 is a prime number, and these are our prime factors for the 81. So we can simply rewrite the 81 as the 4 3's multiplying all inside of that third root radical. And then the order of your radical, in this case of 3, will tell you how many of the same number we can group together in order to pull out of the radical. And so in this case, we have one group of 3 3's, and so those 3's can leave the radical as one group. However, there's one extra 3, and so that one 3 will remain inside the radical. So in short, the little number that's in the hook of your radical tells you how many of the same number you need in a group in order to leave that radical. And then any extras that aren't in that group will stay inside the radical. And so 3 times the third root of 3 becomes our final answer for this one. So now we try that same idea with 32, and in this case, we're looking for groups of 4 of the same number. And remember, when you're doing the numbers, any combinations that you know multiply to make that number will work as long as you continue to break them down. For instance, 32 could be 16 times 2, it could also be 8 times 4. I'm going to choose 8 times 4 for this one. The 8 can be broken up into 4 times 2, and each of the 4's can be broken up into 2 times 2. And since 2 can't break down anymore, these are our prime factors for this problem. So here's that 32 broken down into the 5 2's, and every group of 4 2's can leave. And so this group can leave the radical as a single 2, whereas this one remaining 2 will stay inside of the radical. And then 2 times the fourth root of 2 becomes our final answer. Continuing that same idea for this last example, now we're looking for groups of 5. The first pair of factors I see is 8 times 8 makes 64. Each of our 8's can be broken into 4 times 2 or 2 times 4, and each of our 4's can be broken into 2 times 2. And so now here are our prime factors for this problem. And again, for this problem, we're looking for groups of 5 of the same number, and so these 5 2's can leave the radical, while that one remaining 2 will stay inside. And so 2 times the fifth root of 2 becomes our final answer for this problem. So now let's see the variables. The good news with simplifying radicals with variables is that this part is even easier than doing the numbers because we don't have to think of what numbers multiply to make it. We can just start by breaking our variable up based on the exponent. So this r becomes 5r's. And again, we're looking for groups of 3 for this problem. So one group of 3 r's can leave the radical, and this time we have 2 r's left inside. And this is a case where we can use our exponent of 2 to say that there are 2 r's remaining inside. And so r times the third root of r squared becomes our final answer. Again, following that same idea with this example, if you'd like to, you can skip the step of writing out all 11 v's, because if we know we're looking for groups of 6, we can break that 11 up into one group of 6 v's and one group of 5 v's, because 6 plus 5 is 11, which means this one group of 6 v's can leave the radical. And now these 5 are not quite enough to leave the radical, so all 5 will stay inside. And we get v times the 6th root of v to the 5 as our final answer. And again, following that same idea with this one, we're looking for groups of 8 n's, and we have 10 inside. So instead of writing out all 10 n's, we can write one group of 8 n's and another group of 2 n's, because 8 plus 2 is 10. And then this one group of 8 n's can leave the radical, and then these 2 n's will stay inside the radical. However, here's where this problem might get a little tricky. If you remember from a previous video about how to convert between radical form and fractional exponents, the number that's currently the exponent will be on top of the fraction, and the number that's the root will be on the bottom of the fraction. And so those 2 extra n's we can rewrite as n to the 2 over 8, and then that fraction can simplify, because if we divide both 2 and 8 by 2, we end up with n to the 1 over 4. So technically this is a correct answer for this problem. However, since we could rewrite this as a fraction and simplify it, that simplified form of n to the 1 over 4 could be rewritten as the fourth root of n to the invisible 1. And so this would be the most simplified version of that question, which is more likely to show up as a test answer. And so that last bit of this example can get a little bit tricky, so you may want to watch that a couple times to make sure it makes sense. And as always, they can layer a few of these concepts together to make the problem seem more challenging, but remember, we're just doing the same thing as before as long as we can break it apart piece by piece. So for this example, we're looking for groups of 4, and if we start by splitting up that 80, one combination is 8 times 10. 8 can be broken up into 4 times 2, and that 4 can be broken into 2 times 2, and our 10 can be broken up into 5 times 2. And since 5 and 2 are both prime, here's our 80 fully broken apart, and so here's how we can rewrite that 80. And again, we can either break our x's into 8 different x's, but since we know we're looking for groups of 4, we could also break it into 2 groups groups of 4, because 4 plus 4 is 8. Same idea with our y's. We can break this into 9 different y's, or we could break it into 2 groups of 4 and 1 group of 1 y's, because 4 plus 4 plus 1 is 9. In groups of 4, we have 1 group of 4 2's, 2 groups of 4 x's, and 2 groups of 4 y's. And so those can all leave the radical. Our 1 5 and our 1 y do not have enough to leave the radical, so they'll just stay inside. 2x squared y squared times the 4th root of 5y becomes our final answer. Let's give our last one a go. We're looking for groups of 3. And remember, if your times table still needs some practice and you're allowed to use a calculator, any even number can be divided by 2, so we can just plug this in. And 54 divided by 2 is 27, and 27 is also 9 times 3. 9 can be broken up into 3 times 3, and so these are the prime factors for 54. Here's the 54 rewritten, and just like our last example, we know we can rewrite this as 9m's, but we know we're looking for groups of 3, and so we could rewrite this as 3 groups of m to the 3. We could split up the n to the 10 in the same way, because n to the 3 times would be n to the 9, so we would just need one more to make it n to the 10. So here's our 54 expanded, here's our m to the 9 expanded, and here's the n to the 10 expanded. We're looking for groups of 3, so this group of 3's can leave as a single 3. Each of these m's to the 3 can leave as a single m, but we can recombine those m's, because m to the 1 times m to the 1 times m to the 1 can become m to the 3. And our n's will do the same thing as the m's. We have 3 groups of n to the 3, and so technically that would be 3 n to the 1's. However, we can combine those to just make n to the 3. Now we have this 2 and this n to the 1 left over, so they will stay inside of the radical. So we get 3 times m to the 3 times n to the 3 times the 3rd root of 2n as our final answer. As always, thanks for watching. Please like and subscribe for more videos. And if this concept was a little confusing, you may want to watch this a few times to make sure you got it down. See you next time.